our joint activity between our Institute of Mathematics, Uzbekistan Academy of Sciences, and Barreira Interior University of Portugal, which is called Non-Associative Day. So in the first part of our meeting, we have 3 talks. And the first talk is by Dr. Zerul Zhang from China. And the title of his talk is Some Results on Novikov Algebras and Novikov-Poisson Algebras. Yes? So,
yes, yeah.
You can start your presentation.
Okay, thank you very much. Okay,
Please.
good morning. Okay, good morning, good afternoon, and good evening. I first would like to thank the organizers, Ivan and Jobia. Thank you very much for inviting me to give a talk here. And then I would like to thank my sectional chairman, Professor Shavkat Arpov. Thank you very much for your help.
You are welcome.
My talk is okay, thank you. My talk is on some results on Novikov algebras and Novikov-Poisson algebras. And it contains 3 parts. Part 1 is about nilpotency of Novikov algebras. Part 2 is about some connections between Novikov algebras and its universal enveloping algebra, its associative commutative differential algebras. And we only consider associative and commutative differential algebras later. So I will just talk about differential algebras. And then a similar connection between unitary Novikov-Poisson algebras and its universal enveloping algebra. We call it special Novikov-Poisson admissible algebras. The connections are quite similar to that for Novikov algebras and differential algebras. We shall see soon. Sorry, I recently got COVID, so in the talk I may have some cough. I hope you would not mind. Thank you. And an algebra is called left Novikov algebras. Sorry. If it satisfies the following 2 identities, the first one is called the left symmetry, because here the left-hand side is an associator and the right-hand side is also an associator. And in this associator, we can interchange x and y. So we can interchange the left-hand 2 letters. So it's called the left symmetry. And the second identity is about right commutativity. Here, the right-hand side, y, z, we can interchange them. So this is the right commutativity. And this algebra is found by Balinsky and Novikov, also independently by Gelfand and Dorfman. Zamenhof proved that every simple finite-dimensional Novikov algebra over a field of characteristic 0 is just one-dimensional, so it is a field. And Filippov constructed first examples of simple infinite-dimensional Novikov algebras over fields of arbitrary characteristic. And for simple finite-dimensional Novikov algebras over a prime characteristic, so it can be finite dimensional. Osborne has a lot of work on the classification of simple Novikov algebras with an idempotent element and over a field with prime characteristic, and they study modules over Novikov algebras in a series of articles. Then Xiaoping Xu, a Chinese, gave a complete classification of finite dimensional simple Novikov algebras and their irreducible modules over algebraic closed field with prime characteristic in a series of papers. Then there are also some classifications on low dimensional Novikov algebras. Some of them have some certain given Lie algebra structure. And this bar is also our speaker today. The first part on the potency of and solvability of Novikov algebra is joined with Ivan Shestakov. we study the solvability and the right nilpotency of Novikov algebras. We show that these two notions are basically the same. We first introduce some notation on solvable and right nilpotency and nilpotent. It's normal definition as some other non-commutative algebras. So n to the power of square n to the power of 0 is defined to be n, and n to the power of n with bracket is n minus 1 multiplied by n minus 1. So this
Sorry, any questions? Go on, please.
Okay, thank you. So n is called solvable if that of index n, if n is the minimal integer such that n to the power of n with bracket is 0. So this is the same as if we define solvable Lie algebra and so on. Solvable Leibniz algebra is the same definition. And n is called right nilpotent if every element of length n, but the brackets are from left to right, it's 0, then it's called right nilpotent. Here we use a strange notation here with L here means in the elements the brackets are from left to right, and we follow the notation of Djumididef. Then about nilpotent is means that if an algebra is of nilpotent of index n, if any element of length n is 0, so this one is with arbitrary bracket. And Zamenhof proved that if n is a right nilpotent finite dimensional left Novikov algebras, so if this Novikov algebra is right nilpotent, then n square is nilpotent. This result is similar to that for Lie algebras. And Filipov proved that left Novikov algebra is left nilpotent. If it is left nilpotent, then it is nilpotent. So for left Novikov algebra, the notation of left nilpotent is almost the same as nilpotent. Djumididef and Tulenbev, they proved that for left Novikov algebras over a field of characteristic P, and its right nil of bounded index. If it is right nil of bounded index, which means that a to the power of n is 0, and the brackets are from left to right, and the characteristic is 0 or the characteristic is big enough, then n square is nilpotent. So this result is a little bit generalized that of Professor Zamenhof. So we put it with their name. And if n is right nilpotent, so n square is nilpotent. In particular, if n square is nilpotent, then n is certainly solvable. So in this result, if n is right nilpotent, then it is solvable. And we will prove the conversely. It is well known that every finite dimensional Lie algebra, if L is solvable, then L square is nilpotent. So this is for Lie algebras. And Chilinsev proved a similar result for alternative algebras, not necessarily finite dimensional, but the characteristic not equals 2 or 3. Shestakov proved Chilinsev's result with a simplified method. Okay, so it means that this study of nilpotency of L and L square is of short interest. And similar results for Jordan algebra are also proved by Zamenhof and his co-author. So we prove that if n is a left Novikov algebras, then the followings are equivalent. So if n is right nilpotent, or n square is nilpotent, or n is solvable, so these three conditions are equivalent. In particular, if n is this one is similar to that for Lie algebra. And the equivalence of right nilpotency and solvability is applied in the study of solvability of graded Novikov algebras by Ubinbaf and Jayabin. So they apply this result to prove some new result. As corollary, we also show that if a Novikov algebra can be written as the sum of two solvable subalgebras, then N itself is also solvable. And to prove this result, we prove the other result because they are the same. If A, B are, so if a Novikov algebra can be written as the sum of two right nilpotent subalgebras, then N is itself right nilpotent. This second claim is more easy to be proved because in a Novikov algebra, we have right commutativity. And then when we prove right nilpotency, it's more easy than that to prove the solvability. These two corollaries also have some similar result for, it's a similar result of the theorem of Kagel, who proved that an associative ring represented as the sum of two nilpotent subrings is nilpotent. And Chilintsev generalized Kagel's result for alternative algebras, substituting the nilpotency to solvability. So our result is something a similar result of Chilintsev. Here, we also recall that Novikov algebra is abelian if the product is trivial, and N is called metabelian if it's an extension by if an extension of two abelian Novikov algebras. So if we write the identities, is equivalent to this one. And the following is called the so-called Ito's theorem for Novikov algebras. It says that if A, B are abelian and N is the sum of two abelian subalgebra, then the whole algebra is metabelian. This result has many similar results, such for Lie algebras, Leibniz algebras, and so on. And we also know that if A and B are nilpotent, then and N is the sum of two nilpotent subalgebras, then in general, N is not nilpotent. Here is an example that let N be a two-dimensional algebra, and FA and FB, F is the field. FA and FB are two subalgebra of N, and FA, FB are nilpotent, but they are even abelian. But the whole algebra is not abelian, not nilpotent, sorry. Then we also study linear potent Novikov algebras. This is in some of part work of joint with Ivan, Franz Ivan and Frederick Meshlov and Chen Jiangnam. An algebra is called Lie admissible if the algebra with respect to the commutator is Lie algebras. And this A with the commutator is called the associated Lie algebra of A. A natural problem is that if we know some structure or some information about the associated Lie algebra of a Lie admissible algebra, then what can we say about the original algebra? So our study is okay. So we shall study linear potent Novikov algebras. Sharma and Srivas, okay, they prove that if A is an associative algebra of a field whose associated Lie algebra is solvable, and if the characteristic is neither 2 nor 3, then the ideal of A generated by the commutator is nil. So here they study associative algebras, and they assume that the associated Lie algebra is with some additional condition, say solvable, and they can have they can say something back to the whole algebra A. And Lillet proved that for an associative algebra over characteristic P not 0, the ideal of A generated by commutator is nil. Here they prove that it's a bounded index if some more conditions is assumed. For example, if the associated Lie algebra is nilpotent or solvable with characteristic not true. And we prove that here I do not write the authors and years because the article is still under review. And let n be a Novkov algebras, and if n with respect to the commutator is nilpotent as a Lie algebra, so it's Lie nilpotent, then the ideal generated by the commutator is nilpotent. So it's nilpotent in the sense of as a Novkov algebra. For associative algebras, we do not have similar results, and we know this result from Yabin, and the example is constructed by Chilingsev. Let A be a Grossman algebra generated by infinite set. Then A is Lie nilpotent of index Lie because any commutator lies in the center of A. But the ideal of A generated by commutator is not nilpotent because we have infinite set, and so it's easy to see it's not nilpotent. So for associative algebra, it's not so nice as Novkov algebras in this case. Then we talk about embeddings of Novkov algebras and Novkov partial algebras.
אני כרגע מעדכן, אני הולך עכשיו להתקשר למוסך ולקבוע מתי הם יביאו אותו. אני צריך גם...
understand.
תודה, אני צריך גם... במקרה לפני כמה ימים, רותם עושה לי רשימת תקלות באוטו שלה, שהיא מסיעה בו את טלי. אז זה נראה לי נכונית כדי להסתובב במוסכים.
This is your question. Uzi, Vishne. This is your question or what? Oh, I don't understand. So go on, please.
Okay, thank you. So embeddings of Novkov and Novkov partial algebras, we shall first talk on Novkov algebra case. For embedding, we have to introduce the universal developing algebra of Novkov algebras. It's about associative commutative differential algebras. So D is the derivative. And A with respect to dot is an associative commutative algebra. Whether with the unit is okay. And for all x, y, this D is a derivative. And Zumidi-Dev and Lovewell constructed a linear basis of free Novkov algebra using cheese and proved that every free Novkov algebra generated by a set can be embedded into the free associative commutative differential algebra generated by the same set. And after this article, there are a lot of studies on the combinatorial aspects of Novkov algebras. Here is an example of a Novkov tableau. Novkov tableau consists, all the Novkov tableaus consist of a linear basis of free Novkov algebras. Here, I think we do not have time to explain all the conditions, but we can have a feeling of the basis. Sorry. Here, every monomial has has some block. So this one is a block, and I will explain the bracket. Here, R means that we multiply everything from the right hand side. So we multiply this first, and then multiply this one. So this is R means that the brackets are from right to left. And here, left means that for the block, the bracket of the block are from left to right. So it's like this. Okay, so in every block, the letters I colored them in two colors. The blue color is called leaves by Zumidi-Dev and his co-authors, and the red colored letters are called root. So if we draw them in a picture, and this is the red colored letter, and the other letters are here, and so they are called leaves. And for the leaves, we can order them with a fixed order. We can make it decreasing or increasing, but we must fix. Then for the blocks are decreasing in the length because we can use right commutativity, and then we can fix the length decreasing. And also some other conditions. So for example, here is a condition, but we will not explain too much condition here. We just know that it can correspond to a tree, or we can correspond to a Young diagram here. And then we fix the diagram with some letters here with some condition, additional condition. Then such monomials are called North-Cope tabulas. Well, at least we can have a feeling that this basis is not trivial at all. And we call it a, well, this is a North-Cope tableau with some condition, all the conditions described here, but I think in this talk we can skip it. And S.I. Gelfand pointed out that every associative commutative differential algebra is a North-Cope algebra, which if we define this new product, and we use this notation North-Cope X to denote the free North-Cope algebra generated by X, and Kx define the free differential algebra. Then Kx with respect to the circle product here is North-Cope algebras. And by the definition of universal enveloping algebra, we can see that this differential algebra can be the universal enveloping of North-Cope algebras. Another problem is that whether every North-Cope algebra can be embedded into its universal enveloping, and we shall study it. We did know by D0 A to be A, and the basis of the differential algebra consists of this one. So DI1 A1 to DIN AN, AI are letters in X, and we can fix fixed order because it's commutative, so we can order them. And then for every monomial, we can define a weight. The weight I define here is the number of operators D minus the number of operations, the product. So the number of D minus the number of product. Then we did know by D0X all the set of monomial, the set of all monomials of weight D, weight 0. Then this one form a linear basis of the North-Cope subalgebra of this differential algebra generated by X, and we denote it by N0X because its weight is 0. If we span a subspace spanned by this set, we'll form a subalgebra, and it's called the North-Cope subalgebra of weight 0. Then it turns out that if we define a morphism phi from North-Cope X to, this is the free North-Cope algebra, and to the differential algebra, then defined by phi A maps to A, then this this homomorphism is injective, and then we know that free North-Cope algebras is isomorphic to the sub-North-Cope algebra of Kx, generated by all elements of weight 0, so spanned by all elements of weight 0. And in this way, in fact, we have another basis of free North-Cope algebra consisting of all monomials of weight 0. Well, I think this basis is more easy for computing. And Dovzhenko, Ismailov, and Umibov, they recently studied polynomial identities in North-Cope algebras. They use this embedding and also another embedding, but they use this basis consisting of weight 0 because it's more easy to compute. they show that Novkov algebras over a field of characteristic zero satisfy a non-trivial analytic is PI if and only if it is least solvable. Well, this is very surprising. And we prove that with our co-author Borgut and Chen, we prove that every Novkov algebra can be embedded into its universal developing differential algebra. And if we want to construct it, then the Novkov algebra with generators and relation S, then we can construct the universal developing algebra in this way. Okay. This result has a similar result for Novkov super algebras. So we can show that every Novkov super algebra can be embedded into its universal developing differential super commutative algebras. Super commutative in this way, in this sense. So xy is almost equal to yx, but with the coefficient. And D is derivation of parity 0. And another direction of generalization of Novkov algebra is recently obtained by Kolesnikov and his co-author. They call it non-commutative Novkov algebras. Well, but it's not real non-commutative Novkov algebra. Every Novkov algebra is basically non-commutative. But they are studying something else. And they call it non-commutative algebra because that here we study associative commutative differential algebras, and in Kolesnikov's study, they delete this commutative condition, and so they are studying something embedding into associative differential algebras, and they have very similar way here. Well, people interested in them can find this article in arXiv. It's a very recent paper. And then we talk about Novkov Poisson algebras. We already know a Novkov algebra is an algebra satisfying left symmetry and right commutativity. And Xiaoping Shi defined Novkov Poisson algebras in the way that they have two operations, circle and dot. And A with respect to dot is an associative commutative algebra. A with respect to circle is a Novkov algebras, and they has this compatible condition. The first one is a little bit like the associativity. It's just a little bit like that. And the second one, the order of the bracket of the operation is a circle and then dot. So where circle and dot. And if we ignore the operation, then it's something like associator. Well, it's left. It's like left symmetry, so it's just like it. And we only consider unital Novkov Poisson algebras. So it's Novkov algebra. It means that it's with unit, with respect to the product dot. It does not mean that non-unital one is not interesting. It just means that for non-unital one, we don't know even the free object. Okay, so unital one is more easy for us. And an example of Novkov Poisson algebra is as follows. For every differential algebra, if we define this product, so we already know that A with respect to circle is a Novkov algebras, and A with respect to all the operation is a Novkov Poisson algebras. And for Novkov Poisson algebra, unital Novkov Poisson algebras, we can construct linear basis for free object, and it contains two parts. Part one is a commutative word, and part two is a Novkov tableau. But well, the letters have some condition, but we will not explain here. We just know that it contains a commutative word and a Novkov tableau with some conditions on the leaves. Well, okay, and in the proof we need this important lemma. It says that if we multiply two monomials, then for the second one, we can remove most of the elements. So A1 to AN, we can remove most of the letters. But the price is that we have to add a unit here. And if for non-unital Northcott Poisson algebras, this method does not hold, and because this formula does not hold. So we need to find some new methods for the study of non-unital one. And we can prove that the set of all Northcott Poisson tableau over the set X forms a linear basis of the free Northcott Poisson algebras. So here, free unital ones, I forgot to write, free unital Northcott Poisson algebras. And to prove this theorem, we need to introduce a new algebra called special Northcott Poisson admissible algebras. It's a generalization of differential algebra. We shall see soon. Here, special Northcott Poisson admissible. Well, first of all, why call it this name? Because later we shall prove that every unital Northcott Poisson algebra, let's say NP algebra, can be embedded into such an algebra. And so similar to that for Jordan algebra or something like that, they call it in this way. So we name it in this way. It's an algebra. They have two operations, dot and star, and a well, this D is not a real derivation. We shall see. A with respect to dot is an associative and commutative algebra with unit E, and A star is also a commutative associative algebra. And with the condition here, here it's sort of like associative with, so with any break, any operation, any product is associative. And this D with star is a derivation, but this D with respect to dot is not a derivation, and it has a very strange tail. This part, well, this I'm very puzzled with this part, but when we study it, we find this part is useful here, and we don't see anywhere we can use this. So this identity, it's already for many years, but it still puzzles me a lot. And let A be a special Northcott Poisson admissible algebra. If we define this product, then it becomes a Northcott Poisson algebra. So this one is similar to that of differential algebra. And this is for about the special Northcott Poisson admissible algebras. It says that we can move the bracket, and the second one says that we can move the bracket, and we can also move the letters. And so well, this one says that we can move the operations, the brackets and letters, anything. So it turns out that a linear basis of this special admissible algebra consists of something like this. We can move all the star at the beginning, and the letters are decreasing. So this part is similar to that basis of differential algebras, but the difference is that we may have two kinds of product. And so this is more complicated than differential algebras. And then we define the weight. The weight of a monomial here is the number of operations D, the number of operations D minus the number of operations star. So this is also a generalization of as that for differential algebras. Then for MP0, we mean the subspace spanned by elements of weight 0. And it turns out that this part is exactly the free Northcott Poisson algebra. So if we define phi to be a morphism from the free non-Cartesian algebra to this one is the free special non-Cartesian admissible algebra we defined before, and it maps by A to A. Then this phi is injective, and this free non-Cartesian algebra is isomorphic to the zero part, so the weight zero subspace. And in particular, we find in fact two linear bases of this free non-Cartesian algebra, because another one is in this special non-Cartesian admissible algebra. In fact, I think the second basis is more easy for computing. Well, this part is not necessary for today. And we can also show that every non-Cartesian algebra can be embedded into its universal enveloping special non-Cartesian admissible algebra. The proof is similar to that for non-Cartesian algebras. We just need to consider the ideal. So here, we need to consider the ideal, and we can show that in the universal enveloping, the ideal, it consists of something that of weight zero, and so it's not very difficult to prove the embedding. And we also define a notation that turns out to be interesting, a differential non-Cartesian algebra. It's something like this. If x with this circle x on the left hand side, it's something like a derivative. So x circle on y and then x circle on z. So it's a derivative. So we call non-Cartesian algebra satisfying this identity differential non-Cartesian algebra because this one is like a derivative. And for differential non-Cartesian algebras, if we define df to be E circle f, then this d will become a derivative, and a dot with respect to d will becomes a differential algebras. So we can see here that differential non-Cartesian algebras, Cartesian algebras, and differential algebras has some connection. Because on the other hand, if on a differential algebra we define this one, we already know that it is a non-Cartesian algebras, and it is in fact a differential non-Cartesian algebras. Then, sorry, I'm sorry. If the algebra under consideration is with unit, then and if it is a differential one, then we can prove that it is exactly a differential algebra. So if we consider differential non-Cartesian algebra with the unit, then it is exactly differential algebras. And in this way, from this point of view, non-Cartesian algebras are in some sense a generalization of differential algebras. Kolesnikov and his co-authors constructed a linear basis for differential non-Cartesian algebra without unit when they studied dual Gelfand Dolphin algebras in 2019. And then we introduce a little bit on transposed Poisson algebra because it has a little bit connection with non-Cartesian algebras. Let L be a vector space with two bilinear operation dot and the Lie bracket. The triple is called a derivation transposed Poisson algebra or transposed Poisson algebra for short. If L with respect to dot is an associative commutative algebras, and L with respect to the commutator is a Lie algebras, and they satisfy this identity. This one 2z with this multiply Lie bracket is something like a derivative, but this is called a one half derivation because if this two we delete here, then it is half here. So this is a half derivation. And our friend Ivan has a lot of study on transport Poisson structure using this half derivation. If L is a Novikov-Poisson algebra, then we define the Lie bracket by the commutator. Then L with respect to dot and the bracket is a transport Poisson algebra. So they had some connection. And a transport Poisson algebra is special if it can be embedded into a Novikov-Poisson algebra with respect to the commutator product. And if it is called D special, if it can be embedded into a differential algebras, because we already know that every differential algebra defined by F circle G equals FDG. We already know that by this product, it is a Novikov-Poisson algebras. So in this way, it becomes a transport Poisson algebras. And so transport Poisson algebra is D special if it can be embedded into a differential algebra in this way. And clearly, every D special transport Poisson algebra is special because this differential algebra is also not Poisson algebras. So our friends Ivan and his co-authors has a list of open problems on transport Poisson algebras in this paper. And there are examples of a one generated non-D special but special transport Poisson algebra and a two generated non-special transport Poisson algebras. So an open problem is that is every one generated transport Poisson algebra is special. So can we find one that cannot be embedded into a Novikov-Poisson algebra, or we can prove this one? Well, it remains open. And also it's open to construct linear basis for free transport Poisson algebras. So we need to construct linear basis for this one. Well, the first step may be to find a linear basis for free one generated transport Poisson algebras. As far as I know, it's still open yet. And also another problem is that to find a linear basis of a free non-unital Novikov-Poisson algebras, this basis may have some connection with this one, and it's possible that we can study them together. So recently I'm still working on this way, but not finished yet. Well, that's all. Thank you very much. I'm sorry I talked too fast today.
Thank you very much, Dr. Zhang. So any questions? I have one question. So you study several classes of algebras, and you do not expect them to be finite dimensional, yes? It may be arbitrary dimension.
Yes, arbitrary.
And is there any results, for example, for description or classification of some finite dimensional cases of such algebras?
Well, for Novikov algebra over field of characteristic zero, then if it is finite dimensional and simple, then it is just one dimensional. So not so many study on finite dimensional ones, except that some classifications.
So the most interesting cases are when it is infinite dimensional, yes?
Yes, probably yes.
I see.
Okay.
Thank you.
Thank you very much.
More questions or comments? If not, let's thank our
Okay, thank you.
guest, Professor Zhang. Thank you.
Thank you very much.
So we have about 15 minutes before the second speaker. Should we make a break or we can start the second talk? Our second speaker is Dr. Jifeng Liu. Are you here?
Hey, here. Thank you. Hey.
So let us go on, or we shall
Okay.
wait for little. I think all participants are present here, yes? So we can go on with our program, yes? So
Okay,
please
okay,
then
thank you.
post your presentation.
Okay. Oh, yeah. No, okay.
So the second speaker is Dr. Jifeng Liu from China. The title of his talk is Cohomology and Deformation Quantization of Poisson Conformal Algebras. Please.
Okay, thank you. Yeah. Oh, okay.